Hi, my name is Chiquito Crasto. I am your instructor for BTEC 5322 Bioinformatics Methodologies and Applications. You see my name, my email address, and my office is located in Experimental Sciences Building 1 in room 116. So once again, welcome to the class. And there are we talked about some potential changes in the class. There have been more people saying that uh, they're not likely going to show up, so they are just looking for the YouTube videos. So we might actually talk about maybe not having a class in terms of an online discussion, but just having YouTube videos being made available. And then what I will do is just to make sure that we have engagement and interaction, that 2 or 3 hours a week, I'll just sit in my office and you can either do a Zoom or a Google Meets call if you have any questions related to homework or some general questions. I think that might actually not also be a bad idea. I'm just introducing this. I will also send the same information by email because some of you have expressed saying that you're remote and you would much prefer to just access the videos of each lecture asynchronously. Okay, all right. So once again, that is my name, my email address, contacted, and this PowerPoint and any material is also going to be emailed to you. I'm going to begin this discussion by talking a little bit about the nature of science, a little bit about the nature of bioinformatics. Okay. Um, if you are in graduate school, you already begin to have this experience, but I typically develop this class assuming that you've just come out of undergraduate and then this is your first foray into graduate education. All right, so as such, this is what you see in front of you is a Latin phrase, hic sunt dragones, okay, and that is here be dragons. Now, whenever you have uh, when the oceans were being discovered, new lands were being discovered, people were going in these sailing ships, discovering new lands. The name of the American Indian tribe, for example, came because Christopher Columbus, he went to he left he was given an assignment by the King of Spain to go and discover new territories, and he actually landed in the Bahamas. He never really made it to the United States. And because he never really made it to the United States, but he just called them Indians because his primary aim was to go to India. And until Vasco da Gama decided the best way to go to India was to go around Africa, and towards the Middle East, and you would hit the southwest part of India, is when they discovered that the true India, the Indies, as India was called in those days. Okay, now what happened was and you might say, what is the point of this in bioinformatics? I will make this point soon. And so these cartographers would chart the waters based on the ship sailing and the information they began getting. And when they reached the end, like okay, this is where, and now we've not charted beyond this point anymore. In a map, and this is a true map, they would actually call it here be dragons, okay, which would translate in Latin as hic sunt dragones. Now, why do I bring this up? I bring this up because you have to, once you enter graduate school, you begin to enter this area of research. You're beginning to enter this area of charting into the unknowns. Okay, understand that all of science is evolving. All of science is not necessarily. You hear this where people say, "Oh, the science is settled." COVID vaccines, the science is settled. Global warming, the science is settled. You'll have somebody with no science background, somebody from the in media come and can make these pronouncements. Okay, so that is a lot of charlatanry associated with that. The science is never settled. The science is always evolving. We're making new discoveries, and we are making these discoveries in a way that that would we're making these discoveries in a way where we kind of advance the science literally an inch at a time, and then sometimes if a new discovery takes place, if a new hypothesis cannot be proven experimentally, then you take 4 steps back and then another 2 steps forward. Okay, so do understand that the science is never settled. And the reason I want to say this in graduate school is because now you're associated with research. Now you're charting, you're dipping your toes into the unknown, right? And there are dragons, okay? So it's hic sunt dracones, okay? Here be dragons, and which means that you have to be open to ideas. You have to be open to the scientific methodology. You should be open to evolving the science based on what is observable. A hypothesis is great because that actually brings this creative mindset into play, and then it's like, oh, well, that hypothesis was not necessarily proven by experiment or by real life kind of experiential learning, and therefore you take a step back and revise the hypothesis. Okay, because be doing research, whether you're a master's program, in which case the research is limited, or whether you're in a doctoral program. Okay, and I'm going to send you a a very small book by Henry Hazlitt, who's done some really terrific, very pointed instances of information, and this is called Thinking as a Science. It's not immediately required for you to read, but at some point in the midterm or the final, I'm going to have you explicate 1 or 2 chapters or some interesting statements from it. Okay, so keep this at the back of your mind. It's great reading for kind of any budding scientist. Okay, that the science always evolves, but the scientific method is always true. Okay, so hic sunt dracones. Okay, that's where you are. And bioinformatics is not any different. It's about the same. At the Center for Bioinformatics, Biotechnology, and Genomics, we are doing a lot of genomics work. And even the instrumentation, the methodologies, things evolve. Things are, some methodology, some instrumentation becomes defunct because we are discovering more and more. Okay, and nothing is settled. And I'll give you one example of what I mean by something is not settled, and that is kind of the history of the structure of the atom. So in 1803, John Dalton, and I'm just going to kind of briefly talk about this. In 1803, John Dalton came up with this idea of the atom, and he says the atom is just a solid sphere. Okay, that's it. But it's the smallest part. It's indivisible, and it's just a solid sphere. And there was really nothing. And that was it, right? And remember, if you look at those dates between 1803 and 1904, that's 100 years. 3 generations of people lived their entire lives, and most people don't care because nature is nature, but people who were delving into the sciences dwelt with this notion that the science is settled and the atom is a solid sphere. Okay, then you have J.J. Thomson, a Nobel Prize winner, who came up with what is called the plum pudding model. And they understand that the atom now has, though overall an atom is neutral, there is a charged aspect to it. So what he called it was a plum pudding model. And in a plum pudding model, he says, imagine if it were a cake, a big pudding, and that was the entire nucleus, and then the raisins or the plums that were in the pudding were the electrons that were going about to it. Okay, and so that's J.J. Thomson. Then what happens is once things began to take off, uh, we began to the kind of the notion of what happened was settled, and so then people for about 10 years believed, okay, that was the model. And then Ernst Rutherford came and he said that no, the nucleus is a very condensed core. The most of the atom is in the core in terms of its mass. The electrons virtually have no mass in a comparative way, and they are in these elliptical looking orbits. That's Ernst Rutherford. Okay, 2 years later, Niels Bohr came up with this idea that we can think of it as the kind of the Copernican system, where you have the sun at the center of the galaxy of our solar system, and the planets go in these revolving Okay, and then what happens was then these ideas began coming up of, and a lot of it is based in quantum mechanics. That is, there's the uncertainty principle that Heisenberg came up with, and where he says that two things cannot be, the disposition and the momentum could not be measured accurately both together. If one was measured accurately, you lost something in the other, and that was associated with the Planck's constant. Okay, so this is Niels Bohr's model, and all of these theories and ideas and can only work really well when you have um, uh, in simple systems, right? So you could come up with, for hydrogen, maybe helium, but the moment you went to lithium, that is the atomic number 3, all of these theories fell apart. Okay, they didn't work, which means there was more. And then you had these potential elliptical orbits. There's something called a Sommerfeld's extension, and then you had, Erwin Schrödinger, who basically used this notion of uncertainty and basically came up with this idea of this pushing this idea of the particle wave duality. Okay, and so what you see here is, and to this day we don't really know how an atom really behaves. All these theories, quantum mechanics, using the photoelectric effect. Einstein came up with a whole bunch of ideas, so we don't really understand it. Okay, but again, it's been close to 300 years, more than 300 years after John Dalton's first thing. And if somebody had decided that the science was settled, then that would have been it, right? So the science is never settled. Okay, and again, so this has nothing to do necessarily with bioinformatics, but I just wanted to kind of, as budding scientists, you really have a true sense of what is really going on. Okay, all right, let's go back. So that was just an illustrative point. So once again, here's information. Here's my TTU address. Here's my Gmail account, my office number. Um, I actually respond to emails a lot quicker than I might respond to a phone call. Okay, I'm not having any fixed office hours, but in this case, if everybody is open to just asynchronous learning, I'll have just an open house where somebody can you can if you're remote, then you can contact me and just say, hey, hey Chiquito, let's can I schedule something because I don't understand something, or can you clarify something? And during that time you can just drop by. If during other times you want to drop by, just email me and just say, hey, I'd like to come by, I don't have time to come during your office, that specific allotted time, kind of an open house, but can I come at another time? And that's perfectly fine. Okay, at the end of it, what I'm looking for is engagement, learning, and you walk away enriched by learning something that you've likely not been exposed to. All right, what are the topics covered in this class? Today we're just going to introduce bioinformatics. Today is going to be a really frustrating class because today we're going to have a class where we're really actually going to, I'm going to take you through the struggles of what it means to define bioinformatics, how it differs from computational biology, how, what is a bioinformatician? How does that differ from what a bioinformaticist is? So that we're not really going to arrive at any definitive answers, but I think this is a great way to determine, um, you know, again, it talks to the evolving nature of science. Okay, then you're going to look at classical bioinformatics. We're going to go from, in the 1990s when bioinformatics first became all the rage. We're going to look at, it was a lot of sequence based, and after sequence based, you're like, okay, once we deal with sequence, now let's begin to deal with the genome. Okay, so this is at the genomic level. We're going to talk about high throughput sequencing methods. That's the next generation sequencing. I'm going to look at two specific things and show you some data and take you through the process of how the analysis is done without delving into the kind of the in-depth analysis. We're going to have a midterm. It's going to be take home. Again, if we go with the asynchronicity of this class, then the take home midterm works perfectly well. Depending on how I construct the midterm, you are going to have, it's going to take you, I might have you do this over the weekend, or depending on how I think that the midterm questions are more involved, you might end up taking. I might give you a week. Okay, we're going to introduce you to biostatistics. This class is more an introduction to statistics, but it's more of a statistics, more of a teaser into biostatistics, and we have a really good biostatistics courses at the Nutritional Sciences Center, and also in the Department of Biology. And when it comes time to this class, I will, give you the links to those classes in case you want to kind of develop your biostatistical skills. Okay, we're going to look at proteomics informatics, which is structural proteomics, mass spec analysis, metabolomics, just briefly. And in that proteomics informatics, we're also going to talk about structure, the nature of proteins, and things like that. A brief class on the introduction to clinical informatics, and then there is something which I touch on in terms of my personal research, which is a little bit of just a bare bones introduction to machine learning, to artificial intelligence, to kind of how information is processed, some of the terms that are typically used, what they mean, etc. Okay, and then you're going to have a take-home final. All right, so once again, we will not, let me make this a little, we will not use Blackboard, so don't say I went to Blackboard, I didn't find anything, because you will not. I will communicate everything you need to do by email, so at least check your email once a day, because that's something I noticed that, that a lot of information tends to get neglected. I'm very good with emails. Sometimes you will get an answer in minutes, okay? Again, the files will be emailed to you whenever I make a video. For example, this video, it'll all be available for you on, and a link will be sent to you. Okay. Now, in terms of the grading, I'm not going to, just weight it. This is just some fundamental guidelines. At the end of it, what I'm going to do, I'm going to take all the homeworks, all the midterms, all the finals, everything, and I'm just going to use it as a lump number, and then I'm going to just scale it depending upon my impressions. And once again, don't fall for this. The grading is like, oh, 85% is A or 80. I mean, depending on the student, depending upon the level of the class, the level of difficulty, depending on how you guys compare with each other. Somebody with an 80 will also get an A. Okay, so I'm not going to be one of these people. And this is something to also understand, that undergraduate notion of, okay, 90 is A, 80 is B, and is 70 is C. I don't do that. Other people do that, but I kind of, things change class by class. And what I eventually realize in my class lectures is that eventually, based on performance, students will generally cluster in the little groups of 2 and 3 and 4. This is a relatively small class. When I teach this class in fall, it's typically about in the last few years it's been 30-35 students, so they will fall into these clusters of 2 or 3 or 6 or 7, and then assigning the grades are easy, because all these grades become nicely separated. Do I understand this is a graduate level course, so anything in a C and an F is considered a fail, in the sense that it bring down your GPA, and remember, in graduate school you have to maintain a GPA of 3. All right, what is the class participation? Now, in this, if you're going to do this asynchronously, then this might not necessarily lie. On the other hand, if you have a question that is not directly aimed at me, but is more class related, uh, then just CC your entire group, and you'll see an email where I send it to the entire group. So say, and that's something you might want to talk about. If you submit your exams early, the first 2 will get some bonus points. Okay, so if I see somebody asking questions, somebody challenging me, somebody forcing me to go back to the and look something up because I don't know the answer right away, all of these are actually good things. Okay, any kind of leadership that you show in the class, and I know that's hard, but again, to be in graduate school, depending on where your career is going, eventually you might be in a situation where the buck stops with you. And when I say the buck stops with you, it means what? It means that when you were an undergraduate, or whether you in high school, you went to a teacher, right? When you are in a work environment, you went to your boss. Well, with a graduate degree, you might have, either you will be the ultimate boss, or you might have people who turn to you for answers. Okay, and so this all of this is kind of, it's a, yes, you're learning bioinformatics. Yes, you're learning bioinformatics within the context of biotechnology, but there's a holistic aspect to your training, and you're also training for leadership. All right, so homework, I will assign these. There typically will be involved questions, not something that you're going to be able to solve in 2 hours like it were a quiz, because we're going towards the asynchronous thing here. We will resources, it might something that might take you several hours to do. Okay, you will everything is not just the homeworks but even the exams. You can send it as a Word document, or you can send it as a PDF. It doesn't matter. Word is better because what I can do is it's easier for me to edit your Word document, though PDFs are also easily editable right now, and then just send you the answers. So if I have comments, etc., I can make it, and everything that you submit will be sent back to you. The academic misconduct is something that I take extremely seriously. Okay, if you are assigned to do something in pairs, you work in pairs. If you're assigned, and typically because all of you are so remote and all scattered, I think that I'm going to not have anybody work in pairs, but you're going to work individually. You will work by yourself at all times. If you have any questions, if you have any difficulties, you will bring them to me. Okay. Um, Sometimes what happens with homeworks, I'm completely open to just, you sit down together and help each other out. That's not a problem during homeworks, not acceptable during for midterms and the finals, okay? But once you discuss it and help each other out, then you go off by yourself and you work on your homework. You do not uh, work on your homework together or submit the exact same thing, okay? I will find out it's a small class and then bad things happen. Okay, so you will work on the take home and the midterm final alone with no consultation, except if you have any doubts, any clarifications need. And now, sometimes I'm really appreciative if something is not clear and a student brings it to my notice, then I'll say, oh crap, I didn't realize this. Now let me just send it off, and let me just inform the rest of the class, and a note of acknowledgement and thanks to this person, to the student who brought something up. Okay, there are penalties if I find that you've copied after I have uh, 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 had a discussion with the parties involved. If it's a small thing, you'll get a 0 on the homework. It could go up to an F on the course, and we can have an academic misconduct issue that becomes so egregious that there's expulsion from school. We haven't really expelled anybody yet, but certainly we have had 2 or 3 instances in the last few years where students have had to uh, have been given an F in the course. Okay, and an F in the course is pretty devastating to your GPA, and there's a whole bunch of issues that arise from it. Okay, all right. Having said that, let's go directly into bioinformatics. That's why you've taken the class. All right. So let's look at the origins of bioinformatics. Let's look at the origins of bioinformatics, and I guess the earliest reference would be from the computational biology you know, in uh, 1978 is the first time where they mention. And if you look at this, and again, I'm not just going to read whatever's in the slide. That's for you, but I can kind of contextualize and editorialize and read where things are necessary. So what I've done is, so I'm going to read this quote. However, it seemed to us that one of the defining properties of life was information processing in its various forms. For example, information accumulation during evolution, information transmission from DNA to intracellular and intra and intracellular processes, and the interpretation of such information at multiple levels. At a minimum, we felt that information processing could serve as a useful metaphor for understanding living systems, right? And so that's kind of the point. We look at bioinformatics now. A few years ago, somebody told me, oh, they don't call it bioinformatics anymore, it's data science, right? So it's almost, I have a master's in data science, and this in data science, and that in data science, right? So it's all about information processing. So the reason I like to call this as the origins of bioinformatics, though they've never really used the word bioinformatics, is because they look at a living system as information processing. But very important, they say that the information is not processed, but it's almost like the data has been in place, and that takes care of the genetics, the evolutionary aspect of the information. Okay, and so that is a quote from kind of the roots of bioinformatics by Pauline Hogeway. I'm not sure I'm pronouncing that correctly. All right, so of course, then you have people who have different opinion of when the bioinformatics word came up, and so you have a disputed origin where it says uh, that the bioinformatics is used to encompass almost all computer applications of the biological sciences, but was originally coined in the mid-1980s for the analysis of biological sequence data. And that is, what we're going to do from the next, I think probably next two classes, where where sequence analysis, right? And then eventually, currently, we took the sequence and said, let's take the sequence and extend it to the genome, extend it to millions of, billions of sequences, okay? And so there's a disputed origin that somebody says in the 1980s, but the person in the previous slide said that it was really published in 1978. Okay. All right. Now more disputed origins. Now somebody says bioinformatics. Again, this is not. If you look again, the reason why I started with the Here Be Dragons slide is because I want to tell you that there is nothing cut and dry. Okay. So you have to kind of actually have a mindset, just kind of revisit your mindset when it comes to these things. Okay, that nothing is in stone, things are disputed, things are based on a matter of opinion, things evolve based on how many, and even to this day there might be some people who will absolutely stick to their definition and will not budge from it. Okay, and so this is, it's the nature of the nature of human beings. And so again, so more disputed. So somebody said the term bioinformatics, somebody said that the term bioinformatics arose in the literature in 1991 and in the context of electronic publishing. Okay, and then you have in the rest of the article, you say developing algorithms now, because trying to now define what it is, and making biological discoveries began since the 1960s. So it was called molecular evolution, but the term bioinformatics was not really used. Okay. All right. Now let's look at the definitions. And I know you're not supposed to use Wikipedia as a source, but hey, let's just use it. And I'm going to use as many different sources, and it tells you. And what you're going to see here is you're going to see a struggle, and the struggle is going to be trying to take bioinformatics and fit it into a definition of bioinformatics uh, that is as concise as possible. But then it's like, well, this is concise, but am I missing this? Am I missing that? Am I missing this? Am I missing that? So then you say, okay, let me add that to make it more accurate, and add this part that I might be missing, and add that part. And then what happens is that then it becomes your definition becomes extremely long. Okay. And so this is going to be the struggle, and you're going to see it all the time. It's a struggle between trying to have a definition that's concise and having a definition that is all inclusive, and then you run the risk of the things going on forever. All right. Okay, so let's look at the interdisciplinary field. So this is Wikipedia. It says develops methods, software tools for understanding biological data. As an interdisciplinary field of science, bioinformatics combines computer science, statistics, mathematics, and engineering to analyze and interpret biological data. Now, none of these definitions are false. Okay, when I say it's a struggle to define bioinformatics, to kind of fit bioinformatics into a particular, none of these definitions, they just come from different perspectives. Okay, even if you look at bioinformatics, in terms of how scientists define it, very often they're going to define it in terms of their own kind of their narrow scope or their area of research. And I'll give you a kind of a funny anecdote about this. Uh, I don't know whether you've heard of this, the story of the six blind men from India or six blind men from China, depending upon the origins. And it says there were six blind men, and they were asked to define an elephant, and they were supposed to touch the elephant and find out and kind of describe the elephant. The problem is that one of them touched the side of the elephant, and says, "Oh, the elephant is like a wall." Somebody else touched the trunk of the elephant and says, "Ooh, the elephant is like a snake," right? Or somebody touched the tail of the elephant and said, "The elephant is like a rope." The other one blind man touched the ear of the elephant and says, "The elephant is like a fan." And then another one touched the leg of the elephant and said that the elephant is like a pillar. Okay, so what happens in bioinformatics is the exact same thing. It is you define the bioinformatics based upon a very narrow perspective, and that narrow perspective could be, well, I'm doing work in genomics, so for me bioinformatics is genomics. Okay, the genomics applications, bioinformatics application to genomics analyses, genomics data. Somebody else might be working in proteomics. Some people might be just doing purely theoretical work where they just said, I'm going to conceptualize and come up with creative hypotheses for everything. And that's their definition of bioinformatics. Okay, so none of these are wrong as such, but I just want to kind of give you a sense of the perspective and the struggle that people go to in order to define bioinformatics. Uh, and so, so now we have the question as that, is this definition of bioinformatics generic or specific? Okay, so once again, generic is trying to make it all encompassing, all inclusive, and specific is trying to make the definition of bioinformatics, you know, very, very concise while trying to make sure that that concise definition includes everything. I've said this several times, but you'll see this is an oft repeated theme. So now we have two other definitions, right? So bioinformatics derive knowledge from computer analysis of biological data. The rest of it is the same. And it covers informatics, statistics, mathematics, chemistry, biochemistry, physics, and linguistics. Now here's where they throw in something else. It has many practical applications in the area of biology and medicine, and that is clear. We have a whole new area of study called as clinical informatics, okay? And I will dedicate one class to discussing what clinical informatics. That itself is an evolving thing, and that itself is huge. There is this American Institute, the AMIA, American Medical Informatics Association, which is just in there. You have clinical informatics and developmental informatics and nursing informatics, and so it's pretty widespread. So again, so as you go through this, see if you can come up with a more concise definition. Okay, and so linguistics is, so you might say, why linguistics? Linguistics is the study of language, the evolution of language, language structure, etc. And then you have to ask yourself, the scientific study of language and its structure, including the study of morphology, syntax, phonetics, semantics, where does biology come in? Now, I gave you a teaser that one of the classes will be a special topics based on knowledge management, and in there we will discuss some of this and where it could be applied to bioinformatics or biotechnology. All right. Oops. And so there are other fields, for example, medical imaging, image analysis, which might be considered part of bioinformatics. And then there's a whole other discipline of biologically inspired computation, genetic algorithms, AI, neural networks, all of which will find a place in. And the quickest thing for you to, those of you who have used PubMed, and I'll show you how to use PubMed, would go in there and put artificial intelligence, put in machine learning, put in neural networks, and you'll get a whole bunch. And I'm talking about articles measuring in the several thousand uh, of of articles related to these topics, which you would typically say, wait a minute, where is the biology, where is the biotechnology, where is the biomedicine in any of this? Okay, but it's there. All right, so now we talk about what's called a tight definition, where you want to try and make it very concise. And this is Frege Tekaya from the Institute Pasteur, and the mathematical, statistical, and computing methods that aim to solve biological problems using DNA and amino acid sequences and related information. Now here you see, I've highlighted related, I've changed the color on it simply because what are we doing with related information? And related information just means that you struggle, right? You struggle because you've got DNA, you've got amino acid sequences, that means you've got the protein. Related means now, if he included all the related information that was in this thing, then it ceases to be a tight definition. It ceases to be a concise definition. Okay? All right, let's look at the NIH. Okay. So we'll see. So again, so they talk about bioinformatics is a field of science in which biology, computer science, and information technology merge into a single discipline. There are three important subdisciplines within bioinformatics: new algorithms and statistics, with which to assess relationship among members of large data sets. We're not done. And then there's another whole bunch of, that definition doesn't end. And so I've replaced a significant part of that definition with ellipsis, right? The three dots here, and then we go with the rest of the thing, which is very much about the same, right? And so other definitions, you go to these, a lot of these search engine type things came about as bioinformatics, computational biology, mathematical information techniques, structure prediction, which something we do, system biology, protein-protein interactions, virtual evolution, Now these again, so these definitions, so there's several of these. There were like a lot of these search engine type things came up, and so all these definitions is a lot of thing is based on computer databases and algorithms for the purpose of speeding up and enhancing biological research. All right, so you've got another conference, biotechnology conference. The definition came out of there. Biologists use computers, or the other way around, or computers use biologists. Is that what they're trying to say? So bioinformatics is more of a tool than a discipline. Now some people will say, those of us who do practice bioinformatics, not just from an application standpoint, but from a developmental standpoint, now it's a tool, right? So a lot of people say, oh, it's about building tools, and if you come up with any hypothesis, then that's going to be an issue. All right, so the Webopedia, another wiki thing says the application of computer technology to the management of biological information. Specifically, it is a science of developing computer databases and so a lot of databases, a lot of algorithm. And yes, I have personally been involved with the development and the maintenance of a database that I've been maintaining for 25 years. So yes, that falls under the category of it. But that's not the only thing, right? And so once again, you can include everything that bioinformatics entails in terms of applications and development, but then it's like a definition that never ends, right? On the other hand, you might have a concise definition, and you said, "But I'm missing this and this and this and this," right? So again, just more of the same. BITS Journal, Bioinformatics is a combination of computer science, information technology, and genetics to determine, analyze genetic information. So bioinformatics is the application of computer technology to the management and analysis of biological data. Okay. All right. So you've got other definitions. So now we have the dictionary definition. You can go to Merriam-Webster dictionary, and it says applies to molecular genetics and genomics. And again, I'm not reading this, so I've highlighted the things that I want to talk about. But you can read this at length too. The Oxford English Dictionary. Molecular bioinformatics is a conceptualizing biology in terms of molecules in the sense of physical chemistry, and applying informatics techniques derived from disciplines such as applied math, computer science, and statistics to understand and organize information on a large scale. In short, bioinformatics is a management information system for molecular biology and has many practical applications. So if you look at this, many practical applications, that basically, it just sends it out into the unknown. Okay, so there's another person, Mark Yerstein, who I I've was in the same institution as a faculty when I was a postdoc, and so he uses the Oxford English Dictionary, was supplied by a paper, and where did this information come from? From this particular resource. Okay, it's published about close to 23 years ago. So bioinformatics is conceptualizing biology in terms of macromolecules, right? So that's the definition, and that the Oxford English Dictionary picked it up from here. So again, Mark Gerstein, from the same paper, came up with his group came up with a new idea and methods in informatics, and that is we can call it the depth of bioinformatics, which is the eventual aim is rational drug design, which is kind of like the physics, and then you have the breadth, which is the homologs, large-scale surveys, and informatics. So the way I've conceptualized this is I've looked at it in two parts. Okay, it's a combination of genomics and proteomics. I'm just explaining this. I'm not necessarily saying that this is the right definition, but it seems pretty good. So what happens is you have a genome sequence here, and you go to the original sequence, and then you do a pairwise comparison, which is your classical bioinformatics, and then you do multiple alignment, and then you store this information in databases, etc. Right, and then you have, you look at the golden rule in molecular biology. You have a DNA going to mRNA, mRNA going to protein. So now you have your protein sequence, and you do the exact same thing, right? You can do a sequence alignment, you can do a pairwise comparison, and you can store it in databases. Then from the protein sequence, you look at the structure. Okay, once you look at the structure, then you can look at protein surface, the force fields associated, and so a lot of the molecular dynamics simulations come from this. Then you'll say, well, okay, what is my primary aim? My primary aim is to take a protein, which is a receptor, design a pharmaceutical product which will interact with that protein and produce an efficacious result, right? So for example, a drug is designed to interact with a receptor, with a protein, and then that changes the molecular mechanics of that. It changes the biological pathways and makes somebody with a certain disease better, right? So all of the pharmaceutical industry, the creation of these organic compounds, typically now you can, we also going directly into the bio side of things also, is to work with a protein receptor, change the biological pathways, modify the biological pathways, and kind of fix the defects which are causing a particular symptomatology, right? And so that explains this. Now, there is another term which has come up, and that is called as computational biology. So computational biology, how is it distinguished from bioinformatics, and or should it be? Okay, so again, if you were struggling with trying to come up with a definition of bioinformatics, now you have a kind of a wrench in the works, a spanner in the works, and that is computational biology is another term. Is it the same? Does it mean the different? And now you will see some more struggles with defining it. Okay, so somebody has come up with a Dr. Nair has come up with a computational biology. So bioinformatics plus computers is bioinformatics, whereas computational biology is computers plus biology. Now, what they're trying to do is that you have a biological problem, and the computers are used to solve the biological problem, right? So it's almost like a one is a consequence of the next, one is subsequent to the next, one is a uh, it has to do with the temporality, right? It has to do with the time. That is, first comes the biology and the computers, then you devise algorithms, etc., to solve those problems. In computational biology, he's trying to push this notion that the computational biology is more of the development of ideas or development of hypotheses, and you use computers to do that in order to basically make some sense out of the biology. Okay, that's the definition. So in other words, biologists who specialize in the use of computational tools to answer problems of biology, this is what I said, are bioinformaticians. So first comes the biology, then comes the tools. And then the people who develop theories, develop hypotheses and algorithms in order to understand biological phenomena, not to deal with the data, are computational biologists. Okay? And so again, I'm not saying this is the correct definition, and I'm not saying it's wrong. I'm just saying that people come at bioinformatics and any of the side terms or associated terms from different perspectives. Okay? All right, an aside. What is bioinformatics versus bioinformaticists? So a bioinformatics is an expert who not only knows how to use bioinformatics. So when I say an aside, now another definition is a practitioner of bioinformatics, a bioinformatician and a bioinformaticist, okay? Who likes to write interfaces, somebody who can kind of write software programs, etc., to be able to develop these tools. He's a super user of these tools and also somebody who writes it. But that's a computational biologist, right? Somebody who writes the thing, sort of. And on the other hand, you have the same paper that we looked at. Bioinformatician is so bioinformaticist is a kind of almost like a computational biologist, the one who develops tools. And a bioinformatician is a trained individual who only knows how to use bioinformatics tools without a deeper understanding. So bioinformatician is a user of tools, and somebody might look at this word I'm pointing at, only, and might take offense, but that is what it is. This is what the literature tells you. And a bioinformaticist is an expert who not only knows how to use bioinformatics tools, but also can write interfaces, develop algorithms, come up with ideas. Okay, so is that the correct definition? It depends on who you're asking. Okay, but I'm just kind of telling you what's available here. So here you have Russ Altman. Russ Altman is the guy who developed a lot of the things that you see in GenBank and NCBI. The creation of tools is that solve problems is bioinformatics, and then computational biology is a study of biology using computational techniques. So once again, it seems that the overall notion is what is bioinformatics, what is computational biology. Bioinformatics is develop tools or use tools to study biological problems, right? And computational is use mathematical ideas and novel ideas in order to develop theories and hypotheses about how something works. Okay, so one is downstream of biology, and then the other is kind of a outside view of how to deal with biological problems. Okay, but they're both dealing with biological problems. Okay, so here you have Michael Yu, who says one focuses on computational pipelines and the implementation of theory, which is typically for a computational biologist, and the others focus on purely mathematical and computational theory. So this is again, they are looking at two completely different theories. One is a computational biologist, but again, there's this gray blurring of the gray area, the blurring of the real demarcation between the computational biologists, a bioinformatics, between a bioinformatician and a bioinformaticist, right? It's very gray once again, and it's not necessary to really be able to define it to be able to study it. Okay, that's important. So here's another thing that came from Cornell, that is, broadly speaking, computational biology is the application of computer science, statistics, and mathematics to problems in biology, which is typically what we would, if you had a biological problem and you wrote a software to deal with it, then that's what it is, right? But they call it computational biology. And computational biology spans a wide range: biology, genomics, genetics, biophysics, cell biology, biochemistry, and evolution. And that's the same definition we've been looking at in various flavors for, and then they use things like, machine learning, frequency statistics, statistical physics, Bayesians, which is a statistical methodology. Okay, so again, here's the definition of computational biology at Cornell. And then there was Lincoln Stein, who actually at one point made the statement that bioinformatics is dead a long time ago. Okay, and then of course, he does a bit of a mea culpa and comes back and says bioinformatics is alive and kicking. Okay, and he said bioinformatics is dead not because it was necessarily dead, because it was this big furor that, oh, bioinformatics can solve this problem, and bioinformatics can solve that problem, and it was algorithm development that really hastened the publication of the human genome. It would not have been possible if not for the shotgun sequencing methodologies and the alignments and all of that. It would not have been possible. So, but then what happens was it started with a bang, and then it was, well, where do we go from here, right? It looks like we've solved these problems, and now the problems are becoming bigger because we had genomes. So this was all before the genome. All the genome applications became, every institution now has a genomes application expertise. Okay, so then he does a mea culpa and says bioinformatics is alive and kicking, and then he says biologists are all bioinformaticians now, and that's an important thing too. And this is the last slide. Again, it's a short lecture because it's an introductory lecture. And what are the philosophical underpinnings? And my philosophical underpinnings start a little bit like this. Go from this point of biologists are all bioinformaticians now. Now, if you are a bioinformatics person, right, then let me say bioinformatics is here to stay. It's always going to find new avenues in which you can do development, irrespective of the definition of the domain of knowledge. It's here to stay, whether you like that person's definition or your personal research is more in line with somebody else's definition. It doesn't really matter. The definition of bioinformatics is here to stay, because you're going to find new things. People are going to come up with new ideas. The science is evolving, biomedicine is evolving, biotechnology is evolving. Every flavor which has a bio in it is evolving as our understanding increases. And given the nature of how much information technology is part of our lives, you're going to find a place for bioinformatics. Okay, so how does one reconcile bioinformatics with the mainstay of life sciences, which is experimentation? That is a question you have to ask yourself, and that's where we're going to address in the rest of this course. The reason why Lincoln Stein says that we are all bio is that is what I aim to help each of you accomplish. Okay. Before, what was like, well, saying, well, I'm not a bioinformatics person, I'm just an experimental person, right? And you say, I'm now going to go to a bioinformatics specialist. And certainly there are a lot of times when something like that is called for. But most typical things, right? When you do something, right? Whenever you do something, you need something done, you reach out for your phone, your smartphone, right? Because do understand that because of the accessibility to the internet, this device, which you can put in your pocket, carries with it the combined knowledge of the universe since the beginning of time. Okay, if factually, truthfully, honestly, or objectively put out. That's it, right? And all of you have smartphones. I can't imagine. I mean, someday I'd like to give up my smartphone and go to something a little less smart. But all of you have smartphones and you use it in every walk of life. It doesn't matter whether you want to find a recipe for a meal or a new kind of meal you want to cook, and it doesn't matter whether you want to run some software, right? If the computational capability is available, you're going to be able to use it. And so if you can reach out for to an IT product for almost anything. This is not a phone anymore, right? This is a computer. It's a computer, it's an information source, it's a radio, it's television, it's everything put in one, right? So if that is the case, there is so much, at the last bullet point here says, there is so much web accessibility. So many of the resources are made online, that available online, that you don't really even have an excuse. You can't really say, well, I really don't want to because I'm not a bioinformatics. Certainly, if you've not learned bioinformatics, in terms of programming, etc., then the computational biology aspect of it is maybe kind of beyond your purview because your expertise lies elsewhere, right? But there's so much web accessibility that you can say, I can be a bioinformatician. I don't have to be a bioinformaticist, at least the way we've defined it now. And that's not necessarily the correct definition. But why do you need to go to a bioinformatics person to learn to read a blast search? Why do you need to go to a bioinformatics specialist if you just want to look at a structure of a protein? There's a resource that you can use much primarily because you have the facility of using an information technology product. Okay, and therefore every biologist is now a bioinformatician. You don't have to be a developmental bioinformatician, but you can be a user bioinformatician and progress towards a super user bioinformatician. Okay, so I'm going to leave this here. This is the class. It's about less than an hour, but I think I've covered everything I need to cover. I'll send an email about when we can have that little 2 hour block of time. I'll be doing my own work, but I'll keep it open. I'll open a Google Meets and I'll keep it open. Anybody wants to come, knock on my door. I'll keep that dedicated for any help that you will require. Okay, from next time we're going to start with aspects of classical bioinformatics. All right. So again, this was a first class, little different, maybe a little eye-opening in various respects. So I wish you all the best. Once again, welcome to BTEC 5322.